Oftentimes, when mathematicians model a real-world situation with a mathematical equation, they need to revisit the situation after trying it in the real world and modify that equation. This is true with exponential growth problems. Hi, my name is Tom Atwater, and today we will explore how the exponential growth equation is modified so that it more accurately represents real-world growth. Let's start by learning a technique that will enable us to solve that modified equation. It's called partial fraction decomposition with distinct linear denominators. If f of x is equal to p of x divided by q of x, where p and q are polynomials with the degree of p less than the degree of q, and if q of x can be written as a product of distinct linear factors, then f of x can be written as the sum of rational functions with distinct linear denominators. Let's apply this concept to an example. Let's find the values of a and b that complete the partial fraction decomposition given by x minus 13 divided by 2x squared minus 7x plus 3 equals a over 2x minus 1 plus b over x minus 3. So what we need to do then is realize that we need to clear out the denominators by multiplying both sides of this equation by the LCD. And of course, the LCD is given to us. It's this, which is actually can be factored into 2x minus 1 times x minus 3. So what that gives us is, if we multiply over here, it cancels out completely, and we get x minus 13 equals a times x minus 3 plus b times 2x minus 1. And so, in order to solve for a and b, we need to substitute a value for x that eliminates one of them. For example, if we set x equal to 3, notice that what will happen here is that we get 0 times a, which eliminates the a. So set x equal to 3, and we get 3 minus 13 equals 0 plus b times 2 times 3 minus 1. In other words, on the left-hand side, we get negative 10. And on the right-hand side, we get 6 minus 1, which is 5b. And that tells us that b is equal to negative 2. Now we do the same thing to find a. That is, we set x equal to in this case, 1/2. Because if we set x equal to 1/2, this will be equal to 0. That'll eliminate b. So x equals 1/2. And what we get this time, I'm going to shortcut it, is we get negative 5/2 a is equal to negative 25/2. And that means that a is going to be equal to 5. Now, how does that help us? Well, we now know what both a and b are. So we've taken this fraction, x minus 13 over 2x squared minus 7x plus 3, and we rewrite it as the fractions 5 over 2x minus 1 plus negative 2 over x minus 3. So that gives us what it's called the partial fraction decomposition. Let's explore how to handle a problem when the degree of p of x, the numerator, is greater than the degree of the denominator q of x. And at the same time, we'll show you how partial fraction decomposition can be useful in anti-differentiation. So let's take this problem, which says to evaluate the integral of 2x cubed divided by x squared minus 4 dx. So the first thing that we need to do in this case is when we recognize that the degree of the numerator is greater than the degree of the denominator, then what we need to do is a long division of x squared minus 4 into 2x cubed plus 0x squared plus 0x plus 0. And of course, what we'll notice is we need to multiply by 2x, which gives us 2x cubed. Then we get 0 here because there is no x term to multiply by. Then we get negative 8x, and of course, again, no constant, so that's a 0 there. And when we subtract, those of course add up to 0, and we're left with a remainder of 8x. So that what we now say is that the integral of 2x cubed over x squared minus 4 dx is equal to the integral of 2x plus 8x over x squared minus 4. dx. And of course, we are integrating that entire sum. So our next step is to say that that's equal to, well, we can integrate 2x, that's just x squared. But in order to integrate the 8x over x squared minus 4, we need to do a partial fraction decomposition where we know that the denominator, x squared minus 4, can be written as the distinct linear factors x plus 2 times x minus 2. So what I need to do now is figure out the a and b that allows me to divide that into two fractions. So actually, I think that what we have here is enough that I can just erase that whole board and start with the 8x over x plus 2 times x minus 2, and say that that's going to be equal to a over x plus 2 plus b over x minus 2. And so then multiplying both sides by the common denominator gives me 8x equals a times x minus 2 plus b times x plus 2. And this time, if I set x equal to 2, then I will get 8 times 2, which is 16, equals, and of course, this will be 0 times a for 0, and over here we'll get 4b, so b is equal to 4. Let's now set x equal to negative 2, and that'll give me negative 16 equals negative 4a, and of course this time the b's will be eliminated, so I get that a is equal to 4. So what that tells me is that a is 4 and b is 4, and then I have my two fractions, which I then need to integrate. So what I would have is, remember that originally I had x squared, which had already been integrated. Now what I have is plus the integral of 4 over x plus 2 plus 4 over x minus 2 dx. And of course, we're taking the integral of that entire sum. Again, the integral of the sum of two functions is just the sum of the integral of each individual function. So therefore, I'm going to create some space and rewrite what I get when I take that integral, in other words, anti-differentiate. And what I have is my x squared, which I've had all along, then plus 4 times the natural log of the absolute value of x plus 2 plus 4 times the natural log of the absolute value of x minus 2 plus c. And I can do a little bit of an algebraic manipulation with this, which would give me x squared plus 4 times the natural log, and then in parentheses, the absolute value of x plus 2, let me make that a little longer, times x minus 2 inside absolute value bars, close the parentheses, plus c. So that would be my final answer to the original integral right here, which I found by using partial fractions to help us to find that particular integral. All right, that was great. Now, let's take a look at another type of problem, which is solve the differential equation capital F prime of x is equal to 2 over x cubed minus x. And let me tell you that this is the most laborious type of problem as we will get into. And it involves finding 3 partial fractions. So let me set this up. What it would look like is that 2 over x times x plus 1 times x minus 1. So you can see that what we'll have is a over x plus b over x plus 1 plus c over x minus 1. And now, what I need to do is multiply both sides by the common denominator. So on the left-hand side, we'll just get 2, and then we'll have a times x plus 1 times x minus 1 plus b times x minus 1 plus c times x plus 1. So again, we need to choose values of x that would allow us to solve for the variables in here. So if I start and set x equal to 0, what I'll get is 2 is equal to. Well, notice that when x is equal to 0, it's going to eliminate both of those terms. And here I'm going to get 1 times negative 1, in other words, negative a, which means a is equal to negative 2. Then let's set x equal to negative 1. If I set x equal to negative 1, no, actually, x equal to negative 1, then what you'll notice is this term right here is going to be 0, eliminating the a, and this term will also be 0, eliminating c, and we'll just have b. So 2 equals. And negative 1 for x here, negative 1 for x there, that gives me negative 2 times negative 1, which is positive 2. So 2b. That gives me an answer for b of equaling 1. And now let's set x equal to positive 1. That would eliminate a because this would be 0, and it will eliminate b because this will be 0, and it will leave us with 2 equals, well, 1. 1 plus 1 is 2, so 2c, and I get that c has to equal 1. So what I'm going to do is simply replace these guys up here with their corresponding elements that we just solved for, and then that would allow me to then integrate both sides. So let me get rid of all of this, remembering that a is equal to 2, negative 2, b was equal to 1, and c was equal to 1. So let me get rid of one more stray mark. Okay, So now we want to integrate both sides. This side I'm not going to worry about. This side is the one that we're going to work with. So what that gives me is negative 2 log of the absolute value of x. Then plus the log of the absolute value of x plus 1 plus the log of the absolute value of x minus 1 plus our constant. Once again, we can do some algebra here and simplify this a little bit. And what we would get is that this is going to be the natural log of the absolute value of x to the power of negative 2 times the absolute value of x plus 1 times the absolute value of x minus 1. Put that all in parentheses to show that that's what we're taking the log of. And then I have my plus c at the end. Well, now it's time for you to try a problem just like that. So let me give you your problem. Find the values of a and b that complete the partial fraction decomposition of 16 minus x over x squared plus 3x minus 10 equals a over x minus 2 plus b over x plus 5. Pause the video while you work on this problem, and when you are finished, restart the video to check your solution. All righty, let's find out how you did on this problem. First thing you'd want to do is multiply both sides of this equation by the LCD, and that's going to give us 16 minus x equals a times x plus 5 plus b times x minus 2. And we set x equal to, let's say, negative 5, and that would eliminate my a. So 16 minus a negative 5 gives me 21, and that's going to be equal to negative 5 minus 2 is negative 7, so negative 7b. That gives me an answer for b of negative 3. Now let's set x equal to 2, which will eliminate the b, because 2 minus 2 is 0. Then 0 times b eliminates that. And 16 minus 2 is 14. 2 plus 5 is 7, so 7a. And that leaves me with the solution that a is equal to 2. So the partial fraction decomposition would be then that we have 2 over x minus 2 plus negative 3 over x plus 5. All right, that's great. Now that we've learned the method of partial fraction decomposition, we can turn our attention to logistic growth. The logistic differential equation for exponential growth can be modeled by dp dt equals kp for some k being greater than 0. And the logistic differential equation continued. If we want the growth rate to approach 0 as p approaches a maximal carrying capacity, which we call m, then we introduce a limiting factor of m minus p. So the equation becomes dp dt equals kp times the quantity m minus p. Let's take a look at what the graph of this logistic differential equation would look like then. What we have is a graph that shows the growth coming up like we would expect. And that what happens, though, as it reaches the carrying capacity, then you can see that it has to approach it as an asymptote. And what I want you to notice as well is that if we look at about the halfway point between where it starts and the maximal capacity, what you'll notice is at this point right here is when the population is growing the fastest, i.e. the slope is at its steepest, which is the halfway point. Let's work an example of where we can use this equation and this graph to help us solve a logistic equation problem. Let's say that we have the dp dt is equal to 0.0002 p times 1200 minus p, where t is measured in years. First, find the carrying capacity of the population, find the size of the population when it's growing the fastest, and find the rate at which the population is growing when it is growing its fastest. Well, this is not too bad because what we'll notice is that the maximal carrying capacity, which is m, in the formula in this case is 1200. So that's our answer to part A. In terms of part B, the size when it's growing the fastest, we just looked at the graph which says when it's halfway to the maximal carrying capacity, that's when it's growing the fastest, which means my answer to B is half of 1200, or in other words, 600. So I've written those down on this. Oh, nope, I didn't write them down on that page, but we know that 1200 is the carrying capacity, 600 is when it's growing its fastest. So therefore, we take this equation and we plug in those numbers so that we have dp dt equals 0.0002 times 600 times 1200 minus 600. When you work all of that out, it works out to 72. And I'm going to put this year, because what's important here is that we're saying the growth rate for this population at the time that it's growing its fastest, which is when the population is 600, it's growing at 72 people per year, but just at that particular time. And obviously it will change, so it's important to write down that it's this year. All right, great. Now, let's take a look at the general solution to a logistic differential equation problem. So, here we go. The general logistic formula. The solution to the general logistic differential equation, the one we just looked at, dp dt equaling kp times quantity m minus p, is p equals m divided by the entire quantity, 1 plus a times e raised to the minus mk times t, where a is a constant determined by an appropriate initial condition. And the carrying capacity is m, capital M, and the growth rate constant is k. And they would both be positive numbers. So let's look at an example where we can apply this formula. We're going to look at a table in a moment, but the table is going to show us the population of Aurora, Colorado for the selected years 1950 to 2003. A, use a logistic regression, which we'll do on the calculator, to find a logistic curve to model the data, and then superimpose that curve on the scatter plot of the population against the years after 1950. Based on the regression formula equation, what will the Aurora population approach in the long run? C, based on the regression equation, when will the population of Aurora first exceed 300,000 people? And finally, write a logistic differential equation in the form dp dt is equal to kp times the quantity m minus p that models the growth of the Aurora data that we're about to look at in the following table. So here's our table for the population of Aurora, Colorado. years after 1950. You know, so starting in 1950, the population was 11,421, and then 20 years later, 74,974. What we do is we plug these into our calculator. And when we do that and run a regression, what we find is this, that the regression formula will be P, the population, is equal to 316,440.7, all divided by 1 plus 23 and 577 thousandths times e raised to the negative 0.103 t. Now, let's take a look at what the graph looks like when we superimpose that regression on the data points that we have from the table. And you can see that it does a fairly good approximation for what we were asked to do. Okay, and then in part B, it's 316,441 people, because the carrying capacity is simply the numerator of that regression equation that I showed you. And that regression equation had 316,440.7, but obviously we need to round that up because we're talking about people. Now, to figure out part C, which is when would the population of Aurora be 300,000, you would have to take that regression equation, which we got from the calculator, and set it equal to 300,000, and then solve for t. And when you, again, you can do that on the calculator, and when you do that, it would be sometime during the 59th year, or what works out from 1950 to 59 years, in the year of 2009, the population should reach 300,000. Okay, for part D, what we need to do is move one more slide. From the regression equation, we know that M is 306, that's the carrying capacity, is 316,440.7, that MK is 0.1026, and that K is approximately 3.24 times 10 to the negative 7. So our equation that we want to plug those numbers into is right here. So we plug in that our K, which is right there. We plug in our M, which is right here. And so the regression equation that we're looking at would be dp dt equals 3.24 times 10 to the negative 7 times p times the quantity 316,440.7 minus p. And as a final step, let's look at the slope fields for this particular regression. And you can see that I have the regression line in red, our data points are labeled there, and then there are the possible answers in terms of the slope field that goes with that differential equation. Now, we have the specific one in red showing for the Aurora, Colorado population starting in 1950 with that number of about 11,000. All right, well, that was a great session today. And in this section, we explored population growth. We explored logistic differential equations and partial fraction decomposition. Be sure to work the exercises that your teacher assigns, and we'll see you next time.